If you watch this short video, you will see that there is rubble coming off of that conveyor belt and landing on top of the pile of crushed concrete, and it is doing so at a very steady pace. So the height of this is increasing at such and so amount per minute, which means then that the volume of this conical pile is also increasing at such and so a rate per minute. When you have two different items changing at two different rates per time, that's called related rates. In related rates, the variables are changing at different rates, but they are all changing to the same unit of time. So everything will be changing per minute or per hour. To solve these problems, we're going to use the implicit differentiation that we just learned, where each variable is changing in relation to the same unit of time. In our first example, we have a manufacturer of handcrafted wine racks has determined that the cost to produce X units per month is given by C equals 0.2 X squared plus 10,000. How fast is cost per month changing when production is changing at the rate of 12 units per month and the production level is 80 units? First of all, just read it through. Then go back and look and see what it tells me. It tells us here that the number of units produced is X. Our function that we are going to work with is given right here. The question asks us, how fast is cost per month changing? That's asking us for the rate of change of cost per time. So the way that we write that is DC, the name of cost. That means we're doing the derivative of C. DT stands for where it's a rate of time. That's our question. It goes on and it says that production is changing at 12. Now remember that production itself was X, but this is the change of production. So what that means is that dx dt is 12, and the production level, now here, this is just plain old X. It's not changing, it's just X. So now we have what we're looking for and what we are given. We're going to take our original equation of C equals 0.2 X squared plus 10,000. And we're going to do the derivative of it using implicit differentiation. It's a little bit different than what we learned in the last section. Every variable, when you do the derivative, you have to write d variable dt. So the derivative of C will be 1. And then we write dc dt equals, do the derivative of the x variable that you have here. That's going to be 0.4x. So you just do your derivative, but then as soon as you write your derivative, you must write d variable, in this case dx, over dt. And then the derivative of the 10,000 is just 0, so we don't need to write that. So if you look, we already have this solved for dc dt because 1 times dc dt is dc dt. So it's already solved for dc dt, which means all I need to do is substitute in what I'm given. So 0.4, our x is 80, and dx dt is 12. Do that multiplication and you will get dc dt equals $384 per our unit of time was month. So the cost will be changing by $384 per month at exactly the moment when the rate of change is 12 in production and production is 80 units. For example 2, we are told the profit function for a product is given by P equals negative 0.04x squared plus 45x minus 15, where x is the daily production. Find the rate of change of production with respect to time when production is 40 units per day and the rate of change of production is 10 units per day. So now that we've read it through, here's our question. Find the rate of change of production. So that means rate of change tells us derivative, and everything is in relationship to time, so dp dt is what we are looking for. When you go on through, it tells you production is 40. So that means x is 40. It's not the derivative unless it talks about rate of change. And when you move forward, it talks about rate of change of production is 10. So that means you know the derivative part for dx dt is 10. So our function being p equals negative 0.04x squared plus 45x minus 15, we need to do the derivative of this function. The derivative of p is 1, but then I must write dp dt equals, the derivative of the first term will be negative 0.08x, but because we just took a derivative, we have to write dx dt plus the derivative of 45x is 45, and we have to write dx dt because we just did a derivative. And the derivative of the minus 15 will be 0, so you are done. This is already solved for dp dt, which is what we're looking for. So we just need to substitute in our numbers. So we're going to have in the first term negative 0.08 times 40 times 10. In the second term, we're going to have 45 times 10. Do all this arithmetic and you will get $418 per day. Example 3 tells us a 25-foot ladder is placed against a building. The base of the ladder is slipping away from the building at the rate of 4 feet per minute. Find the rate at which the top of the ladder is sliding down the building at the instant when the bottom of the ladder is 7 feet from the building. This is a classic related rates question. You see these types of questions frequently. First thing to notice is we don't have a formula to use given to us this time. But let's draw a picture and think about what's going on here. We've got this building, and against the building, we have a ladder that we know is 25 feet long. We're talking about the base of the ladder moving away from the building. So that's a rate of change because it's 4 feet per minute. It's a distance per time. Anytime you have some kind of a unit per time, it's a rate of change. To help keep myself organized, I always let x be a horizontal variable and y be a vertical variable because that's what they are on the x and y axis, and that just makes sense to me. So when it's talking about this ladder moving away at 4 feet per minute, the rate of 4 feet per minute, that's telling me my horizontal change, or dx dt, equals 4. It says find the rate at which the top, so if you start talking about rate at, that means that you are looking for a derivative, is sliding down the building. So we want to know, how fast is this happening? How fast is it moving downward? And because it's a rate, dy dt is the thing we are looking for. And then you are told the bottom of the ladder is 7 feet from the building. Well, what they've given you with that piece of information is that the distance of x is 7. In looking at what we have right now, we know our question mark, and we know the horizontal distance, and we know the length of the ladder. What we don't know is the vertical distance, or where the ladder is hitting the building. At what height does that happen? We are making the assumption here that the ground is flat and the building is vertical, truly vertical. So we are assuming that this forms a right angle, which means that we can use the Pythagorean theorem to find our vertical distance. So our x is 7 squared plus y is what we're looking for squared equals 25 squared. So 49 plus y squared equals 625. Y squared then has to be 576. So y has to be technically plus or minus 24, but this is the height, so it has to be positive. So we now know that y is 24. To do our related rate, we need some kind of an equation to do it for. Anytime you have a right triangle problem, you're going to use the Pythagorean theorem as your formula. So we're going to use x squared plus y squared equals z squared as the formula that we are going to do the derivative of. However, check anytime you're doing one of these right triangle problems. Notice that the length of the ladder is never changing. It is always 25. So it is not a variable, it's 25. So we're going to rewrite this formula as x squared plus y squared equals 25 squared before we even do the derivative. And that's purely because the length of the ladder does not change. If you have a side in your triangle that you know does not change, then that side goes in as that number before you do the derivative. So now I need to do the derivative of my formula that I'm using. The derivative of x squared is going to be 2x, and because it was an x, I must write dx dt plus the derivative of y squared is 2y, and then my variable was y, so we write dy dt equals, now remember that 25 squared equals 625, and the derivative of a constant is just 0. Now let's look at what we're supposed to be finding. We're supposed to be finding dy dt. So the first thing I'm going to do is get that term by itself. 2y dy dt equals, move the other term over, negative 2x dx dt. I'm solving for dy dt, So I'm going to divide both sides by 2y. So dy dt is going to equal, now notice over here, 2 over 2 is 1. So we get negative x dx dt over y. Now that we know what dy dt equals, we're going to substitute in the numbers that we were given. We get negative, our x was 7, our dx dt was 4, and our y was 24. So we get negative 28 over 24, which is negative 1.17. This is a rate of change. How were we measuring our y? We were measuring it in feet, and our unit of time was minute. We got a negative answer. Is that okay? When you think about it, we were talking about on this triangle that this is moving downward. So what is that distance doing? It's getting smaller. So our answer being negative makes sense because that's indicating that that distance is decreasing. For example 4, we have one car leaves a given point and travels north at 30 miles per hour. Another car leaves the same point at the same time and travels west at 40 miles per hour. At what rate is the distance between the two cars changing when the cars have traveled 2 hours? So first of all, let's just get our point. Here's our point. The first car leaves that point and travels north. So they're going up. So this is a vertical distance. I'm going to call that my y. And this is a rate of change. They're moving at 30 miles per hour. So dy dt is 30. Another car leaves this same point and goes west. So they're heading this direction. And that's a horizontal distance, so I'm going to let that be x. And they're telling us that that rate of change in the horizontal distance is 40. At what rate is the distance between the two cars? That's the hypotenuse. Changing when the cars have traveled 2 hours. Because it's asking me the rate of change for this distance between them, that means that the derivative of this side is what I'm looking for. And the variable for our hypotenuse is going to be c. This is still a right triangle problem, but this time all 3 of the sides are changing, and so all 3 of the sides get variables. They didn't tell us anything specifically about x and y, but they did tell us how to figure it out, because we know that these cars have traveled for 2 hours. So the car that was going 30 miles per hour, if they traveled for 2 hours, they went 60 miles. The car that was traveling 40 miles per hour after 2 hours went 80 miles. What we don't know is the variable z, but we can figure that out. We're going to do 60 squared plus 80 squared equals z squared. 3,600 plus 6,400 equals z squared. 10,000 equals z squared. So do the square root of that, and z has to equal 100. Now we know all the parts except for dz dt. That means we need our derivative. The formula we're going to use is the Pythagorean theorem, and this time we are going to use all three sides as variables because all three sides are changing. You actually put in the number if you have a side that is not changing. These are all changing. So do the derivative of each term. 2x is the derivative of our x term. Because it was x, we must write dx dt plus 2y dy dt equals 2z dz dt. Notice that there is a 2 everywhere. So I'm going to divide every term by 2 just to make it a little bit simpler. And now just have x dx dt plus y dy dt equals z dz dt. dz dt is what we're trying to find. Right now it's being taken times z. So we need to divide both sides by z, which gives us x dx dt plus y dy dt over z equals dz dt. So now we need to substitute in our values. Our x value is 80, our dx dt is 40. Our y value is 60, our dy dt is 30, and put that over the z of 100. If you do that calculation, you will get dz dt equals 50 miles per hour. The rate of change between the two cars was 50 miles per hour. On example 5, a sand storage tank used by the highway department for winter storms is leaking. As the sand leaks out, it forms a conical pile. The radius of the base of the pile increases at a rate of 1 inch per minute. The height of the pile is always twice the radius of the base. Find the rate at which the volume of the pile is increasing when the radius of the base is 5 inches. We are talking about the volume of a cone. This is not a formula that most of us have memorized, so I have given you the formula for volume of a cone. Anytime you need to use a formula like that that is not that commonly used, I will give you the formula. Let's go through and look at what they are telling us here. They are telling us radius of the base increases at a rate of. So, dr dt is 1 inch per minute. Moving forward, the height is twice the radius. So they are telling us that h equals 2r. Question, it says, find the rate at which volume is increasing. So dv dt is what we're looking for. And then it just says radius is 5. So we are told r equals 5. Now, when you look at the formula for volume, there's an h in there. And the information they gave us about is r's. So what that tells me is that I cannot have that h in my formula when I do the derivative. But they did tell me how h and r are related to each other. So the first thing I'm going to do is take my volume formula. I'm going to leave the r squared in there, but I'm going to replace the h with what I know it's equal to, which is 2r. Next, I'm going to clean up this formula so it's a little bit easier to do the derivative of it. If I take the 2 times the 1/3, I get 2/3. I'm going to keep the pi. R squared times r gives me r cubed. Now I have a formula that has only r and v in it. And that's good because the only derivatives I knew were for r, and v is the one I'm looking for. Let's do our derivative. The derivative of v is 1, but we have to write dv dt equals. Coming over to the other side, drop the 3 times 2/3. That's going to give you just 2 as your coefficient, and pi is a number, so it has to stay in there also as part of the coefficient. The power on r goes down now to be 2, and because we did the derivative of r, we have to write dr dt. We are looking for dv dt, and this equation is already solved for dv dt. So we're going to substitute what we know now. 2 and pi stay in as your coefficients because they're just numbers. R is 5, and we're going to square it. And we are told that dr dt is 1. 5 squared is 25 times 2 gives me 50 pi. And if you actually multiply that out, you get 157.1. Now, how are we measuring this? Inches per minute. But this is how volume is changing. So it needs to be inches cubed per minute. Example 6 says, a spherical snowball is placed in the sun and begins to melt so that its radius decreases at 1/4 of an inch per hour. Find the rate of change of volume when the radius is 4 inches. And again, I gave you the volume of a sphere formula because that is not one that most people have memorized. Looking at what we were given in this case, it is telling us radius decreases at 1/4 inch per hour. Because that is a rate of change, we know that dr dt is, and this is important because it's decreasing, it's negative. I'm going to write it as 0.25. Moving forward, find rate of change of volume. dv dt is what we're looking for. And then it says radius is 4. So r is 4. Our information is about r's and v's, and those are the only variables in our formula, so we can just move forward with the derivative. The derivative of the v is 1 dv dt equals, drop the 3 times the 4/3, you're going to get 4 pi, go down by 1 to r squared, and we did the derivative of r, so we have to write dr dt. We are already solved for dv dt, which is what we were looking for. So we're going to have 4 pi times 4 squared times negative 0.25. Do that calculation, you get negative 16 pi, which is negative 50.3 inches is how we were measuring our size, per time was hour. Again, this was volume, so it needs to be cubed. It was how volume is changing. Does it make sense for this rate of change to be negative? Think about what's happening. The snowball is melting. It's getting smaller. And so because it's getting smaller, the negative makes sense. It's telling us that it's decreasing.